Usama Mahmoud, Scott Smolka, and Scott Stoller, and we're all at Stony Brook University. So this talk, it builds upon runtime assurance architectures, in particular the Simplex architecture, which we've seen some talks this morning with sort of related setups, where the idea is you have sort of something that looks like kind of like a standard control loop. So you have a controller and a plant, and you have this sort of closed loop interaction. And typically the way the system operates, it's sort of like this, where everything is sort of transparent. But in order to add some safety to the system, you also have this sort of backup controller, which you call a baseline controller. And the decision module monitors the state of the plant, and then it switches to the baseline controller. If at some future state, it's possible there'll be you get close to violating safety. And so this is the original Simplex architecture, but there's some downsides to this type of setup. And so the one we'll focus on today is talking about the baseline controller itself. There's formalisms in the paper. I won't go into too many of them in the talk, but we assume the sort of discrete time model where, given the state, an input from one of the controllers and potentially a disturbance, and if we're considering disturbances, you have some nonlinear function that computes the next state of the system, and sort of proceeds in this fashion. So what's stopping the Simplex architecture from being more widely used? And so one drawback is the baseline controller must be provably safe. You need it as a backup. So if it's unsafe, your whole system will violate safety. So this means you can't typically use things like model predictive control, where you have complex cost functions or nonlinear differential equations, because this relies on solving global nonlinear optimization problems online. And typically you have some trade-offs between exploration and exploitation, and there's some randomness involved in how those are solved. So you can't guarantee that you'll always find an optimal or even a good solution. You can't use things like rapidly exploring random trees, because again, that relies on some randomness. So you can't statically verify algorithms that use RRT. So those couldn't be used as baseline controllers. You couldn't usually use things like neural networks. So I'm interested in verification of neural networks, and certainly there's been progress in the field, but I'd say for sufficiently complex networks, you really couldn't verify that the closed loop system is safe using current technologies. You couldn't use controllers that are safe 99% of the time. So if you come up with a really good algorithm that works well, you still wouldn't want to use that as your backup controller if there's a chance that it'll fail. At least you couldn't guarantee safety in that particular case. So sort of a key problem that we consider here is, could you modify the Simplex architecture to not have this requirement of a verified baseline controller? So to have sort of a backup baseline controller, let's say it's safe 99% of the time. Could I still use that in a way that guarantees safety 100% of the time? So before we get into the solution, what are some properties you would want for a system using Simplex? The first one is you would want safety, which is that the system can't enter an unsafe state 100% of the time, right? We want full correctness, assuming that the models are correct. So of course, even if you're developing a controller using control theory, you have this assumption that you have models of your system. So if the models are wrong, you can't make guarantees. So there's some assumption about models. But that's sort of not enough. So in the original Simplex architecture, you can have safety by just always using the baseline controller. So what you really want is this other property as well, and this we call transparency. So this is saying that when things are going well, and we'll define well a little bit. It's defined in the paper more formally, but I'll explain the intuition a little bit later. The system looks like the advanced controller is actually the only controller in the system. So this prevents this case of just using the baseline controller forever and satisfying the types of properties we want. So for this work, we make this additional safety assumption about systems, that there's some states where you can maintain safety forever and it's sort of easy. So we call these permanently safe states. And of course, this is very specific to a type of system, so it's easier to go through a couple examples. So if you have an autonomous car, at the moment that you're sort of parked on the side of the road, that's a permanently safe state. For a package delivery drone, maybe after it's executed its emergency landing and it's sort of on the ground resting, that's a permanently safe state. Maybe you have a fixed-wing aircraft swarm that's moving very quickly, and it's sort of too fast for humans to be able to take corrective actions when problems occur. So then a safe state under that sort of set of assumptions, you could just have the drones fly in non-intersecting circles, and this will slow down the what's going on in the system so that a human can take control and issue corrective actions. If you have a multi-robot collision avoidance system, so this will be one of our case studies, we'll consider this to be safe if you have all robots that are moving away from each other, and then presumably if you keep the acceleration at 0, you won't have a collision into the infinite future. And more generally, if you're looking at control theory, if you have a nonlinear system and you're in the basin of attraction of a stable controller, and the states in the basin of attraction are safe, this could be a way to guarantee permanent safety into the future of the system. So the intuition with black box simplex, how it works is that you have this sort of system invariant that there's always a backup plan that can get you to one of these permanently safe states. So the way the system works is you have the advanced controller, it generates some command, which will tell you what the next state of the system would be. You'll be able to make a prediction. Then the baseline controller, what it tries to do is generate a backup plan from the next state. And so this backup plan is what gets you to the permanently safe state. And then the decision module's responsibility is to check the generated backup plan. And if it's actually safe, then you can store it for use at the next step. And if anything fails or takes too long, the decision module always has that backup plan. So that's sort of an invariant that you've had this backup plan, you computed before. And if any of these things don't work, you just execute the current backup plan. The picture of the system looks something like this. So here, you can start with the advanced controller. It produces a command. The look ahead baseline controller now takes that command and produces a command sequence that gets you to a permanently safe state. Then it passes that to decision module, which actually checks that this command sequence does what it's supposed to do. And then if that's true, it'll store the command sequence for use later. And then the command sequence importantly starts with the command that's given by the advanced controller, so that the first command that actually gets sent to the plant is the one from the advanced controller. And then the rest of the commands are sort of backup plan. And then at the next iteration, the advanced controller will generate another command, and then the look ahead baseline controller will again try to generate a backup plan. And this sort of continues forever in this fashion. So in the paper, we have two theorems about this. The first one is the safety theorem. And so what this one is saying is if you start off, initially safe with a initially permanently safe command sequence, this is this backup plan, then the system guarantees safety regardless of the advanced controller and the look ahead baseline controller. So these can even be incorrect. And you just look at the interface of them, you don't have to look at the internals. The second theorem is the transparency theorem. And so what this one says is that from the current state, it basically states the conditions under which the advanced controller gets to actually actuate the plan. So what it says is if the advanced controller produces a command that actually has a backup plan, the look ahead baseline controller is sort of strong enough to be able to generate that backup plan. And the decision module is strong enough to be able to check that backup plan and sort of guarantee that it's safe and everything works fast enough. Then the command that gets sent to the plant under those assumptions will always be the one from the advanced controller. So the whole system sort of works transparently from that perspective. And so does this actually work? So there's two case studies that we go through. The first one we call multi-robot collision avoidance. The setup is sort of here. You have a bunch of robots that start out initially on a circle. And every robot has a goal state that's across the circle. So this robot here in red has this goal state, which is this blue cross here. So it tries to go across the middle of the circle. So if you just go straight, everyone will collide in the center. And this one has sort of very simple dynamics. There's positions and velocities, and the control commands are the accelerations. And the velocities and accelerations are the magnitude of them are bounded with some maximum value. And the strategy we take to solve this is a model predictive control formulation. And so there's both for the advanced controller and the baseline controller. We use model predictive control, but we have separate cost functions for the two controllers. So the advanced controller, what it tries to do is maintain separation. This is sort of like a potential fields approach. So it combines two terms. You have the separation term. You want to stay away from everybody else, and you also want to minimize, get close to your target. So it's a get to target term. So it's the sum of these two terms. The baseline controller also tries to maintain separation, but instead of trying to get to the target, its goal is just to sort of get out of the circle. So it has a sort of a simpler goal that hopefully is easier to solve than the one that advanced controller is trying to solve. And then for optimization purposes, you combine this cost function term from the previous slide with a penalty on the control, how much control you actually send out. So you don't want to send very high accelerations to the system. And then to actually run this, we use something like fmincon from MATLAB. So there aren't really guarantees that we're going to minimize this cost function. We aren't really going to find all of the accelerations, but it might work well in practice. And we can actually make it fail by limiting the number of iterations that it runs. So in the original Simplex architecture, you wouldn't want to use this, right? Because it can fail. The baseline controller can fail in this case. So here's one example scenario. This is the setup we had before. And so what's going to be shown is the backup plans generated at each step. So the robots are all following the advanced controller's command as long as a backup plan can be generated. So here it's a safe backup plan. And the way we check it's safe is that each of these robots have these sort of green states they'll go into. And if you look at the last state and the direction the robots are moving in, they're all non-intersecting rays. That's the condition we use to check. At the next step after this one, you get this backup plan, which is not safe because here the last position and velocity vector going from that intersects with another robot. So these two robots actually look like they might intersect in the future. So this backup plan is not a safe backup plan. This one gets rejected, and so we'll switch to this backup plan. And so we'll see that in this animation. I'll just let it run through once, and then I'll look a little bit closer at some of the frames. So what was shown here at sort of the very beginning, the robots start at the middle, and you can see that they start moving following the advanced controller commands, and you can see the backup plans being generated. So the backup plans just try to guide the robots outside the circle. And sort of it works well up to here, and then you get this backup plan, which is the not safe one. So then what the robots do is they switch to the previous backup plan and then just execute that, and nobody has a collision. And you didn't really accomplish the goal, but nobody collided, which is fine. It's safe at least. So this could be modified as well too. So here, as soon as we switched to the backup plan, we stayed with the baseline controller's plan. We didn't switch back. You can actually switch back. It's valid to do that. And so that's what we call reverse switching, and that's the next scenario. So in this reverse, in the example scenario 2, it's the same sort of setup with more ground robots. What's shown here is the path of the robots taken when reverse switching is active. So the blue states are parts of the path where it's using the baseline controller, and then it switches back, and so you get more black states. And if you follow each of these, you can see they actually made it to the other side of the circle without intersecting. So here's the animation of that. In this case, when the robots are red, they're following the advanced controller's command. And when they're blue, they're following the backup plan. So that you can see them actually turn a little bit towards the outside of the circle when it's blue. And then when it's red, they go back to following the advanced controller's command. And in this case, because we have this reverse switching now, even though they occasionally use the backup plan, they're all able to accomplish their goal eventually and get to the target state. We can incorporate uncertainty into the system if we wanted to. So the way we do that, there's two ways. You could consider sensor error in your initial position, or you could consider disturbances at each point in time too. So we considered both of those. Since this is a linear system, we could use reachability using zonotopes. And so there's this quick zonoreach library that you can use, which is sort of an efficient implementation for zonotope-based reachability. In this case, there's time varying inputs because you have a disturbance at each step. And this step, the uncertainty is all in the initial states. And so what ends up happening is at sort of the final state here, you get a zonotope with 112 generators. With disturbances at each step, you add more generators to the zonotope. So at the last step, you have 364 generators. But this is still fairly quick. So computers are fast, and this reachability with zonotopes is pretty good. So this is still sort of milliseconds to do these types of reachability computations. So it seems usable. The second case study is collision avoidance in multiple F-16. So the theme of this case study is to make a really hard scenario. And so we'll take several steps to make something that I think would be very hard to try to formally or statically verify for correctness. So the first way we make it hard is we consider a neural network controller. So this is the CAADCPS collision avoidance system. This is actually a pretty popular benchmark in the neural network verification community. The neural network tries to avoid collisions of aircraft by issuing commands. So this is actually the geometry of a scenario. So you have an own ship and an intruder aircraft, and based on their relative distances and relative headings, you feed those as inputs to the neural network. And the neural network outputs what should happen if you're clear of conflict, or whether you should issue a turn command: weak left, weak right, strong left, strong right. And so one question is, why are they using a neural network? Actually, originally the system wasn't designed with a neural network. It was a partially observable Markov decision process. But when you encoded all of the different state variables into a lookup table, it took several hundred gigabytes of memory. And they realized this wasn't going to fit on certified avionics hardware. So they decided to do a compression. And one way to do that was using 45 neural networks that each look like this one: 300 neurons in 6 layers. So this is used as a benchmark for neural network verification. Typically, the properties are open loop properties, which means that given some constraints on the inputs, what can you prove about the outputs? So you could have properties like, if there's an aircraft directly in front of you, make sure a turn command is issued. That's sort of one example from this paper by Katz. But this isn't, this is sort of hard enough as it is, although sometimes you might be able to verify aspects of this. So let's not just look at a neural network. Let's look at something harder, which is a closed loop system that uses a neural network. So here you could have a physical system that looks something like this, where you have the own chip on the bottom and the intruder is coming on top. And now you can see that you have multiple invocations of the neural network over time that tells you which way the own chips should turn. And depending on the initial position of the own chip, you get different command sequences issued. So here was just 5 different initial positions of the own chip for the same intruder. And this system's very hard to, this is sort of much harder to verify because you execute the neural network multiple times. The physical dynamics here are still Dubin's car dynamics, so it's sort of fairly simple. There was sort of semantics as to what strong left and weak left mean. So weak left, I think, is 1.5 degrees per second, and strong left is 3 degrees per second. So you can execute exactly that response using a Dubin's car model. But still, this is sort of harder to guarantee safety, and I don't know of any work that really proved safety for this closed loop system, even with the sort of simple Dubin's car dynamics. But we want to make a hard benchmark, so let's make the system even harder. So how can we do that? So instead of using Dubin's car dynamics, let's instead use a more complicated aircraft model. So in particular, let's use an F-16 simulation model. And so this is a benchmark we published in Arch, which is just taken from an aerospace engineering textbook. And so it's a nonlinear system. It's 6 degrees of freedom. There's 12 state variables for the aircraft, 1 engine lag term, so 13 state variables there. And then I think there's 3 integrators for the low-level controllers. And it's able to do things like fly between waypoints and execute certain maneuvers. But it's a complex non-linear system. You don't have closed form differential equations. This is done using Python code. I think there's a MATLAB version as well. But it would be very hard to verify anything dealing with this type of physical system. So we can combine this F-16 model now using with this ACAS-XU system and get responses that look very similar to the Dubin's car model, which is sort of what you would expect. Although you should keep in mind that here, it looks like it's the same type of response, but behind the scenes, this is, the 16-dimensional nonlinear model where you can't turn instantaneously. The aircraft first has to roll before the heading starts to change. So you have, 16-dimensional nonlinear system for each aircraft here, both the own chip and intruder. Okay, so let's say we have this system now. Let's make it even harder. So this is the last thing that we'll do, which is rather than just having a single aircraft, let's now replicate this. So we have multiple aircraft in our scenario, and we're trying to avoid collisions. So this is a mutual ACAS-XU system, where just like the collision avoidance system with robots, everyone starts in a circle going towards the center. The goal is to fly to a waypoint on the other side of a circle. So if you were to do nothing, all the aircraft would collide in the middle, so it wouldn't be safe. And the baseline controller will be to use ACAS-XU, but of course, ACAS-XU is only defined on sort of a single intruder aircraft. So what we do is we run ACAS-XU against every other aircraft in the scenario. And if there's a turn command issued, we find the sort of closest aircraft that has a turn command that gets issued and use that command. So if everybody's clear of conflict, you can use the advanced controller. If any ACAS-XU issues a turn command, that aircraft will turn. And of course, everybody's doing this against everybody else. So this almost feels like the original Simplex architecture, right? We have this ACAS-XU, which can tell you clear of conflict, and then you could use the advanced controller. Otherwise, you could just use the baseline control, which is follow ACAS-XU. And so the question would be, can't you just use ACAS-XU? Like, doesn't this solve the problem, right? It's almost it almost looks like it would work. And of course, the answer is no, right? So the key thing we wanted to do with black box simplex is remove this assumption that the baseline controller should be statically verified. So here, the baseline controller is not statically verified, and it shouldn't be trusted. And so there's a number of reasons why that is. The first one, the POM-DP formulation, my understanding is that was never formally verified to avoid collisions. There's this neural network compression that goes in with ACAS-XU, so it's not an exact, it doesn't exactly replicate the POM-DP commands. So that's never been formally verified. Also, we're using these closed loop F-16 dynamics, not a perfect Dubin's car model. So that's going to lead to potential problems. You can't turn instantaneously in that type of system. And ACAS-XU was designed for single aircraft collision avoidance. So we have this multi-aircraft scenario, which sounds kind of reasonable, but this is not the way the system was designed. So this is sort of like out of distribution usage for this. And that one leads to a lot more problems. And so we'll see some examples of this a little bit later. But the issue is, I think it'll be very hard to try to formally verify any type of baseline controller for this scenario. So this is just showing how this mutual ACAS-XU is working. So in the two-plane scenario now, both the sort of each aircraft turns against the other one. And you can see that looks like collisions are avoided. So that's pretty good. You can have more complex scenarios, and it sometimes works reasonably, right? So what's shown here is the command each aircraft is issuing, and the line is the other aircraft is trying to avoid, right? So each aircraft can only avoid one other aircraft at a time with ACAS-XU, and you can see which one is being followed. So here in this 5-aircraft scenario, I was actually able to safely navigate it. But it's not too difficult to find sort of harder scenarios. So here's a 6-aircraft scenario where you start to see some of these problems. If you look at these 2 aircraft on the bottom, they actually end up colliding following this type of setup, as well as a couple other aircraft. So this baseline controller is not really safe. But if we adapt this and use this black box simplex setup where we take again, we take the first command from the advanced controller and then follow what ACAS-XU would do and check if it can still guarantee safety, and do this at sort of every control iteration here, we can actually design a system that's safe and provably safe. And so this is now comparing using the original ACAS-XU system versus black box simplex. So in the original ACAS-XU system, even this simple 3-aircraft scenario, you can see here, this is it's showing the frame where the aircraft are closest. So the solid line is the historic path and the dotted line is the future path. And so here there was an aircraft on the bottom, and these 2 aircraft on the top both decided to turn to avoid the bottom aircraft, and in turn they ended up crashing into each other because of that. Whereas with black box simplex, all aircraft, so this is the closest frame, you can see the closest distance is 1,600 feet. And so here I think for the requirement it was 1,500 feet. So they sort of safely navigated this scenario. In the 4-aircraft case, the sort of conclusion we want is that black box simplex is more transparent. So using ACAS-XU, the system safely navigates the scenario. 4 aircraft are able to all get past each other. But the closest distance is 5,000 feet. Whereas here with black box simplex, if we had a requirement as 1,500 feet, the closest distance is a little under 1,600 feet. So it not only navigates the scenario, it doesn't have to deviate the path as much as ACAS-XU originally does. In the 7-aircraft case, we're showing that black box simplex is easily customizable. So originally, if you use ACAS-XU, this is a failure. So it doesn't navigate the scenario, aircraft crash into each other. With black box simplex, we can very easily change the safety distance by just changing the check distance in the decision module for collisions. So if we use a 1,500 feet collision distance, the closest distance is a little over 1,500. If we lower that to 1,000, it's about 1,100 feet. If we lower it to 500, it's about 517 feet. So all of them avoid collisions, and you can sort of change the desired safety distance. So this would be really hard to do with ACAS-XU originally, right? You'd have to recompute the POM-DPs and redo the compression and then redo any verification of the compression that you've done before, but we can do it just by changing a parameter. And finally, the 15-aircraft case, this is showing that we're able to safely navigate complex scenarios. So keep in mind, each aircraft is a 16-dimensional nonlinear system. So this is a 240 nonlinear system. ACAS-XU originally fails in this scenario. There's multiple aircraft that sort of overlap. Both black box simplex, you get this sort of maneuver that looks a little bit like a roundabout maneuver. And so this is an emergent property. This is not something hard-coded into the system, but it's how the system was able to actually solve this scenario. So here's an animation of that case. And you can see the aircraft switching between the baseline and advanced controller. So you can see this reverse switching sort of important. And every aircraft sort of flies by every aircraft without violating the collision distance. So the minimum distance here eventually gets to 1,500 feet. So we'll just watch that one more time. And so the conclusion, so black box simplex, it allows you to build systems using unsafe baseline controllers. And the way it does that is you have more extensive runtime checks, and you have these stored command sequences in the decision module. So the decision module, it's not producing any command sequences. All it's doing is executing these stores command sequences and maybe updating it based on the information provided to it by the lookahead baseline controller. And so this is really neat, because now if your baseline controller is correct 99% of the time, or you don't have a formal proof of correctness, even though it sort of looks like it's working well, you can now use it in practice and still get guarantees for safety. So there's this sort of longer report you can find on arXiv if you search for a safe CPS from unsafe controllers that describes some of these details. Thank you for listening. That's the talk.
Thank you. So there is a question by Bingju.
Yes, so thank you very much for the interesting talk. So I have a question regarding the new architecture here. So if I understand correctly, for the original Simplex architecture, so the decision logic decide between the advanced controller and the baseline controller, decide which one to be fed to the controlling plan. But now, so the advanced controller and the baseline controller get the state from the plan, but there is no connection between the advanced controller to the decision logic. The decision module, instead, the command from the advanced controller is feed to the baseline controller, and then the baseline controller feed and command to the decision module. So my first question is, what is the relationship between the baseline controller and the advanced controller? It is a filter of the advanced controller, or it is something else? Mm-hmm. So this is my first question. And the second question is that, so there is a backups. Actually, the decision module can still provide a backup solution to ensuring safety in case that the baseline controller is not producing something which ensures safety. So what is the difference for my following description? I treat the advanced controller and the baseline controller together as the advanced controller for the original Simplex architecture. And I treat the backup solution in the decision logic as the baseline controller in the original Simplex architecture. So what is the difference between my description here to the new architecture you are proposing here? So thank you.
Okay, yeah, thanks, Bingjo. So the questions are good. So the relation I didn't go over in the talk, which is bad. It's mentioned in the paper though. What the baseline controller produces is sequence of commands, and the first command in the sequence should be the command that the advanced controller has provided. So okay, that's the connection there. So that the decision module, what it's doing then is it's choosing between its stored command sequence and this new command sequence that's proposed by the look-ahead baseline controller.
Okay.
So that's where it's making the decision. And so if it chooses this command sequence, then the command that actually gets sent to the plant is the one that was produced by the advanced controller.
Okay.
And that hopefully helps a little bit with the second question as well too. So the decision module in this case is not generating any of the command sequences. It's just checking and storing and maybe executing them in a timely fashion, right? In the original Simplex architecture, the baseline controller was generating commands that needed to that would need to be executed. Here, the decision module doesn't actually do that. You could potentially put these, because these are both black boxes, right? We're just looking at the command sequence that gets output into sort of one big black box and call that a single controller. I think it's better to have this logical separation, because you can then separate between trying to get to some target in the mission and generating the backup plans. So it's more of a logical separation of concerns that you have. So the baseline controller is always just trying to generate backup plans. You could say, okay, create a single controller that first tries to accomplish the mission for one step and then generates backup plans, and it would be equivalent to. But I sort of like this logical separation a little bit more.
So you means that the decision logic would not create any backup solution. So which component is actually creating the backup solution to ensure safety in case that the baseline controller here is actually producing something that it is unsafe?
Yep. So great question. So what's happening is the decision module has a stored command sequence.
Yeah.
And so this was computed and checked at the previous step, that this is a safe backup sequence from the current state.
Okay.
And so it's choosing between the previous command sequence that was already checked and this new proposed command sequence.
And the previous compute command sequence is already being verified that it is safe for the. Okay.
So it's really the baseline controller is what's generating it, but it generated at the previous step.
Okay, and so it means that the command sequence here are also generated by the baseline controller, but different from the current command sequence generated by the baseline controller, that the previous one has already been proved that it is safe. Am
Yes,
I
that's
understand? Right. Okay,
Mhm.
got it. Thank you very much.
And so the safety proof is sort of by induction on this, right? So you need some initial, at your initial state, you need a safe command sequence.
Yeah.
So that, under that assumption that initially you start out with a safe command sequence, then all you're doing is updating it with other safe command sequences. And so by induction, the system will stay safe.
Yeah, clear.
So,
thank you.
Yeah, thank you a lot, Stan. So I guess that's time for the next speaker.